All right, let's talk about, there's three different types of relationships that lines can have. The first type of relationship is lines can be parallel. This is not new information. Okay, we should be able to recognize that parallel lines never intersect. Now, the part that you may not have thought about before is that those lines are coplanar. So, parallel lines are two coplanar lines that never intersect. For example, D and E. And if you notice at the bottom, there's our notation for parallel lines. We say that D is parallel to E, and the symbol simply looks like parallel lines. Okay, besides being parallel, we can move on to the next thing, which are skew lines. And skew lines are similar to parallel in that they never intersect. However, they're different because they're considered non-coplanar. So they're non-coplanar lines that never intersect. So for example, AB and EF. They are never going to touch each other, okay? But you could never drive a train on them. They're not like railroad tracks. They're not coplanar. So another set would be BH and FG. So I want you to pause the video and write down two more examples of skew lines. Okay, the third relationship that lines can have is that they can be perpendicular. So these are coplanar again, just like parallel. So they're two coplanar lines that intersect to form right angles. So right now we have line A is intersecting line B at a right angle. Notice this is our right angle symbol. And in order to write that lines are perpendicular, we're going to use what looks like an upside down T. Again, it looks like we're showing perpendicular lines. Okay, the second objective for this video is to discuss angles and to recall some knowledge and perhaps shed some light and explain a new postulate to you. So when we have angles, an angle is formed by rotating a ray around its endpoint. So that endpoint is called the vertex. So U is the vertex of this angle, and the rays would be US and UN. Okay, so we said the vertex was U. So we rotated a ray, US, about its endpoint, U. Okay, we can open that up. So in order to name an angle, we can excuse me, we can do that in a couple different ways. We can name it by its vertex, as long as there's only one angle with that vertex. We could name it with a number, if the angle is numbered. We can also use three letters that discuss the rays and the vertex. So you always put the vertex in the middle. Okay, so a non-example would be angle USN. Okay, do not write angle USN. Let's take a look at adjacent angles. And before we define what adjacent angles are, let's identify some angles. So we have angle 1 and angle 2. We could also call angle 1 angle WIS, or we could call it angle SIW. Angle 2, labeled with letters, could be angle SIH or angle HIS. Again, notice that the vertex is I, so when we use the letters, I is the middle. We could also talk about the large angle, angle WIH, or in reverse, HIW. Notice that we cannot use angle I because there are 3 angles with a vertex of I. So since we've identified those angles, let's see if we can determine which ones are considered adjacent. And adjacent angles share the same vertex and one ray, but they do not share any interior points. So there's the vertex, and here is the ray. So the adjacent angles are angles WIS and angle SIH. We cannot say that angle WIS, which is right here, and angle WIH. And the reason that this is not an example is that these angles overlap. They're not adjacent. So the points that are contained within WIS are also contained within WIH. So they would not be considered adjacent angles. All right, this should be pretty easy to recall. There's 4 types of angles. Okay, an angle, we'll call it theta, with a measure that is less than 90 degrees is considered acute. Okay, an angle that is greater than 90 degrees is considered obtuse. An angle that is equal to 90 degrees is considered right, and an angle that is equal to 180 degrees is considered straight. We could look back at these statements and write them as inequalities, and we could say that an acute angle has to fall somewhere between 0 and 90 degrees, and an obtuse angle has to fall somewhere between 90 degrees and 180 degrees. Okay? Similarly to the segment addition postulate, we can work with the angle addition postulate. And it's the same exact thing. 2 adjacent angles can be added together to give us a larger angle. So angle TIM plus angle MIC is equal to angle TIC. Now we should have little m's in front of here, and we will talk about what those little m's mean. So the measure of angle TIM plus the measure of angle MIC equals the measure of angle TIC. And when we do some substitution, we see, if I can make this a little bit larger for you, that a 40-degree angle plus a 15-degree angle is going to give us a 55-degree angle. And we also have something called an angle bisector. And an angle bisector is similar to that of a midpoint because it is going to divide something in half. So an angle bisector is a ray that divides an angle in half. So in this instance, ray AL bisects angle HAF. So we can mark the 2 arcs that are the same, and again we can use these little hash marks to show that they're the same, and we can also relabel this angle. So we want to revisit notation just like we did with segment congruence. We have congruence here, angle congruence. So HAL, angle HAL, is congruent to angle LAF. Okay, so that is how we read that notation. And then if we want to talk algebraically and we want to fill in numbers, we say that the measure of an angle is equal to a number. So the measure of angle HAL equals 30 degrees, And since those angles are congruent, the measure of angle LAF is also equal to 30 degrees. Again, a translation into words reads here. All right, during class tomorrow, we'll do some more practice exercises.